Hello everyone, welcome to our webinar, How to Assemble Low-Cost, Open-Source, Easy-to-Use Air Quality Sensors. This is the first one of the webinar series, Quality Monitoring Powered by Citizen Science. This is a webinar that we are organizing in the framework of the Urban Pathways Project, which is a project funded by the International Initiative for Climate from the Ministry of Environment of Germany, and it's implemented by us, by the Wuppertal Institute, and by UN Habitat, and we are developing this webinar in partnership with OpenSeneca and WRI Brazil. And the idea of this webinar, and while OpenSeneca is still setting everything for presenting you the step-by-step of assembling an air quality sensor. The idea of this webinar, in comparison to the other webinars that we have had, is to have more a train the trainers approach, by which we have identified some partners in cities. Some of them are you listening on the other side, and we have identified some partners that could implement the workshops that OpenSeneca, they will show you in a bit, have implemented on site in Nairobi and in Argentina. And the idea is that we train research centers or fabrication laboratories, maker spaces that have the skills, the knowledge, the capacities, and the interest to develop these kind of things. And they can then conduct the workshops on site with the citizens, with cyclists, and other interested groups, so that the network of air quality sensors grows in the city. In the second webinar that we're going to have, it will be not oriented on the assembly like this one. It will be oriented much more on the uses and the policy that is behind it and what could be done with such devices. We will present some cases of Medellin and Santiago, where they have already implemented programs in a larger scale, on including citizens, because as the name of the webinar series is Air Quality Monitoring Powered by Citizen Science. So it's very important the fact that we include the citizens in this and create awareness about air quality and how can we influence it. So we will show some examples about that. And in terms of like the structure of today's presentation or of today's webinar, it will be conducted by the OpenSeneca team. They will present themselves and the project. That will be the first thing that we'll do. Then they will go directly to the assembling of an OpenSeneca air quality sensor. And in that regard, this will be a very technical thing. We are collaborating with the Fab Lab Newton Paiva. They already, in Belo Horizonte, Brazil, they already got some of the components necessary to assemble one of the air quality sensors. So the idea is that they will be leading the instructions of OpenSeneca and will be able to create their own air quality sensor. And in the case that that could be a little bit too technical or a little bit boring, feel free to leave at this point. You're also welcome to stay. The webinar will be recorded and will be shared with you. So in the case that in a future stage you are able to get the components and obtain all the information that you need, you can obviously see it again and with the components in place and assemble your own device. Then we will see if the experiment really worked. Then we will see if the Fab Lab Newton Paiva, which is our counterpart in Belo Horizonte, was really able to assemble their own air quality device. And after that, OpenSeneca will again lead us to their online platform, where they will show how to use it, how the data is collected and shown, and also the GitHub where all the details of the assembly of the device are and the components and so on that you would need for if you would like to create one. And finally, as this will, like the final objective is that this leads to a workshop on the cities where you are working. The idea is that they will provide us with some tips of the workshops that they've already conducted so that the workshops on site are successful. So I would now give the word to OpenSeneca. I will stop sharing my screen and also my camera so that you can connect yours. Perfect, we can see it. And but we cannot hear you, Lorena.
Can you hear me?
Yes, now I can hear you. So I turn off my camera and silence myself, and you're on.
Okay.
Great.
Go ahead.
Should I go ahead? Okay. How do I click on the slides?
No. You're ready to go.
Okay. Welcome to our webinar on how to assemble our low-cost, open source, and easy-to-use air quality sensor. First, I would like to give you. My name is Sebastian. First of all, first I would like to give you a bit of a background on what air quality sensing is. Okay, and the projects we're doing, our approach, and yeah, how OpenSeneca fits into the whole equation. So air quality has gained a lot of traction in the media just recently. It's titled as the silent killer that kills more and more people, more than what smoking used to be the past decades ago. Unfortunately, it's affecting the poorest in the world the most. If you look at the recent years of Google Trends on the left-hand side here, you can see that air quality has gained 70% of a plus in Google searches from 2015, where just very few people spoke about this topic. It's become much more into the center of attraction now. That's because air quality and air pollution in particular is starting to be seen as a major contributor to certain cancers, strokes, heart diseases. For example, you can see on the right side here, 29% of deaths from lung cancer are traced back to air pollution issues, 24% of deaths from stroke, 25% of deaths from heart diseases, and 43% of deaths from lung diseases. And the system is financially affected by that. If you look at the global healthcare system, the recent numbers say that $5.1 trillion is the global cost of air pollution alone. So we see a staggering 7 million deaths from exposure to air pollution every year. And the worst of all is we cannot really escape it. 91% of the world's population live in places that exceed the WHO guideline limits for air pollution. And the worst pollutant of all health-wise for humans seems to be particulate matter. In fact, if you look at the graph in the center here, you see conflict, terrorism, tuberculosis, malaria, HIV. They all contribute to a loss in average life expectancy per person. But that's just little compared to smoking and particulate matter pollution, which is on the very large end of the spectrum. On average, you lose 1.8 years of your life just to particulate matter air pollution. And that's from a recent study from the University of Chicago. You can think of particulate matter as small particles. You see that in the very small photo on the right top corner here. If you take grains of sand or human hair, which is around 70 to 90 micrometers in diameter, think of particulate matter in much smaller, 10 times an order of magnitude smaller. PM10, which is which is tracked by our sensor, is 10 micrometers in diameter, and PM2.5 is even able to pass into the bloodstream if you go smaller and equal to PM2.5 in diameter. So what is the main problem? Well, the main problem is we have a lack of awareness in the population, and there's very little education about air pollution to date. And that's not only but also because of the lack of personal connection to climate change and air pollution, which is tightly linked together. Because people don't really see the immediate effects of climate change and air pollution in respect to their health. And that's also because we don't really have an infrastructure to secure the healthy environment. We cannot really escape the dust and the air pollution that we're surrounded by in large cities. If you look at the number of reference stations worldwide for air quality, we see there's a lot of air quality reference stations, expensive stations placed in the developed world, in Europe, in the US, North America, also in Asia. But then look at Latin America and look at Africa. There's basically none, and these people cannot really monitor the air they're exposed to, which makes it even worse for the poor people. The solution we were working on is by sharing knowledge through education, by making air quality sensing personal. So you need to be able to monitor the air around you yourself. You need to get a personal feeling for air quality. And of course, it's all linked together by big data. Only if every person, every individual that tracks the air quality around them brings it together and sees it in a bigger context, we can use big data and AI to basically make maps of hotspots of air pollution and inform policy with that. And that's where we come in. OpenSeneca is in line with the United Nations Sustainability Development Goals. We want to use citizen science and empower citizens with it. We are convinced that mobile sensing is the future. Rather than having just one reference station in a part of the city, we want to empower everyone and have mobile sensors that give a very high spatial, but also a good temporal resolution. We are also convinced that open source is the way to go. So everyone can learn how to build a sensor. Everyone can download designs and build their own and also adapt it. We are using co-creation, which is kind of a buzzword, but we think only if people can actually make their own impact on how the sensor looks like, and if people can alter the sensor and adjust it to their local environment, it can be a compatible sensor, like globally compatible, but also locally appropriate if you think of developing countries. And that's why it also needs to be low cost, because everyone should be able to afford an air quality sensor. And we are using plug and play components for that. We talk about a bit more about that later. I would like to introduce the OpenSeneca team. Some of them are here right now, coming over right now. My name is Sebastian. I'm in the center. Then we have Lorena, who is in the bottom left corner of this slide. We have Peter, who's in the bottom center, and we have Chris. And we all do a bit of everything in the project. Some do more outreach, some do more hardware development, but we all did this together. Charles will join us later, and Raf is mainly responsible for the case design and will not join us today. So let's talk about our modular sensor. You can see the sensor we deployed in Argentina on the left-hand side. On the right, you see what's in there. We have a modular PCB that has some form of storage and there's a micro SD card. We have wireless transmission via the 2G network. We have a GPS module. We have a particulate matter sensor, in this case from the Bern Syrian, and we measure temperature and humidity. Some projects we did. Our first international project was in Kenya, in Nairobi, where we embraced on the co-creation approach. We went there for 3 times now for a week to work with the local people in the makerspace, and we adapted and adjusted the sensor and listened to their feedback, worked together with them, and built a nice box. And in the end, we distributed a few sensors in collaboration with the UN and celebrated the whole thing in a big event where stakeholders joined us to look at what we did. We had another project shortly after in Buenos Aires where we worked with the government to deploy sensors on bikes. We deployed 20 sensors overall with a cycling community, and it was a big event that was organized together with the UK-Canada Fellowship. The Canadian ambassador joined us, and we went to 2 universities to build the sensors first, and then had a big launch event again with the government. We collected data in Buenos Aires. I want to speak a bit more about Buenos Aires here because that's where we got a really nice data set from. We collected data over 7 weeks in Buenos Aires with the cyclists, and we were also able to compare our sensors against the US Embassy reference stations in Buenos Aires. You can see the reference station here on the left, and on the right you see a zoomed in picture of 6 of our sensors that were placed on the reference station overnight. So we could see the trend over a certain period and how our sensors compare against the high quality, very expensive reference station. If you look at the data here, I just want to give you a quick snapshot of the data. You see on the x-axis, you see the time, and on the y-axis, you see the PM2.5 particulate matter concentration that was measured. In yellow, you see our sensors binned. So you see an average of these 6 sensors with the standard deviation, and the red dots signify the US Embassy data. And you can see that the trend is actually very similar. So it follows the same trend with some outliers up and down, which is to be expected. But overall, the trend is very similar. If you zoom in a little further, you can see the hourly median of PM2.5 in comparison. What's really interesting about this graph is during that night, the reference station and the American Embassy was not functioning for a couple of hours, while our sensors still took data. So having multiple sensors can be a very good thing as long as the data seems to be qualitatively well in line with that. You can zoom in further and see again it's following the same trend. I just want to quickly go over this. And we then visualize our data in maps. So we use basically the Google Maps API. This is actually not Buenos Aires but Paris. You can see the map on the left-hand side where we zoom in and then look at the street view. And on the right-hand side, you see the time resolution, basically a time series of the pollution that this individual person was exposed to during his commute. looking back to Buenos Aires data, if you then divide the center of the city into tiles of a specific size, and for every tile, you take the data points that contributed to this tile, so all the data points that are in this perimeter, and average them, you get a nice map of the city where you can see hotspots after you remove the baseline. What we call baseline is the background PM concentration that is lying across the city, basically. And we take 15 minutes because that's on average how long it takes for the wind to carry a wave of particulate matter pollution across the city. So in order to see individual highlights of highlighted areas of potential concern, you remove this background baseline, and that's how you end up with these red dots in certain areas. And looking at some of them, zooming in further, you see the tile in red in the center here, which is, not very surprisingly, close to a very big junction, and right next to this junction is a gas station, which might further contribute to the pollution here. So I'd like to hand over to Lorena at this stage. Quickly mention our collaborators in the previous projects that I just talked about, and now handing over to Lorena. Thank you.
Hello, everyone. So now we're gonna, that was an overview of what we've been doing so far, so you can get an understanding of what kind of project and what kind of data we can get with our sensor. Now we're gonna start an interactive assembly. There are 2 of the Fab Labs have sensors with them, so they're actually gonna build with us. If anyone is gonna get quite technical, we're gonna talk in detail about all the components and how to plug basically everything that's necessary to be able to build one of the sensors, and as well, if you are to organize a workshop in your own city, everything you should know to be able to transfer that knowledge to the citizens and replicate a project like the one we did in Buenos Aires in your own city. So if anyone feels, everyone is welcome to join. If anyone feels they don't want to know that much detail, also feel free to leave at this point if you were just interested in the general overview. But that's what we're gonna start with now. So let me show you.
Lorena?
Yeah?
Just a small remark. For the ones staying, please feel free to send your questions via the question box on your control panel. There you can write your questions in Spanish or in Portuguese or in English, the language you feel more comfortable with. Every step will have like a small pause where Lorena will ask if you have questions. There I will ask her the questions that you've included in that box. So feel free. And if there would be any bigger problem with like the Fab Labs that have the components there, we can see if we can activate the microphone or the camera so that you can show the specific problem, and the OpenSeneca team can support you. But for now, the idea is that you post your questions in the question box, and at the end of every step, we will ask those questions to the OpenSeneca team. Yeah.
Yeah, and feel free to write anything, and at any point. This is supposed to be interactive, and we don't want anyone to have any doubts about all the steps. So I hope everyone sees well. So I'm gonna be showing here all the different components. So this is a custom printed circuit board that we designed. It's a very simple one. It doesn't have, it's basically just connections, but it's mainly, as you can see, it has different pins. And the main purpose of that is that because we want this sensor to be built by citizens or Fab Labs or everyone in their own country, we wanted to use off-the-shelf components that are easy to use and accessible to as many people as possible. So we have these plug and play approach. It's a bit like a Lego board, and basically it indicates, it's written in the name in white where each component should be plugged. It should be fairly easy to sorry. Okay, good. So it should be fairly easy to know where each component should be plugged, and we're gonna go through that individually. So that's a custom board we designed. It can be adapted, it keeps evolving. This one was meant to be really for prototyping, so I make it easy. So we have a switch button here to be able to turn on and off. It has a battery inlet here to just plug a normal micro USB cable, and then you can plug it to a power bank. So I've got a power bank here, for example. A power bank is something most people should have at home, so citizens could just provide their own. There are 3 requirements that need to be taken into account. I'm going to talk about all of these details now a bit more. And then integrated modules already on the board we have here. This is a Bluetooth module to be able to communicate to a smartphone app. And then there's a few chips, small chips here. I don't know if you can see this one here and these ones. This one is a temperature and humidity sensor. And this one are just like some electronics to control all the power. So the board is designed, as I said, in a way so it's easy to plug, easy to understand where to put each of the components, but also taking into account that different parts have to be separated. So all the sensors, all the parts that are actually sensing something in the air are in this area. So this is where we are going to have the particulate matter sensor, is where we're going to have, as I said, the temperature and humidity sensor. And we also have a VOC, it's volatile organic compounds that can be related to CO2, to carbon dioxide gas pollutants. And on the other side, we have mostly the transmission and other components. So we want to keep them apart to prevent interferences. I'm going to talk you through each of the components. If you have any questions, please let me know. So if anyone has any questions about the board, feel free to ask, and Rosa will let me know. This is the microcontroller. I imagine most of you are familiar with Arduino. This is very similar to an Arduino. It's the reason why we chose, it's called the black pill. And the reason why we chose this one instead of a standard Arduino is because it has a bigger RAM and flash memory. So we have many sensors connected in this board, so and the code is can be quite big. So we do need enough flash memory to have the coding, and as well we need enough communication ports to be able to communicate with all the sensors. So that's something that needs to be taken into account, and that's not something we could do with a standard Arduino. The other reason to use this microcontroller is that it's very, very low cost. It's only, you can find it here in the UK for like £4. If you get it from China, it's like $1 or $1.5. And I believe also in Latin America is available for a pretty low cost compared to other ones. And Arduino is normally around 20. So that's the microcontroller where we have is the brain of the system. That's what's going to have the code that is organizing and saying what everything else has to do. Then we have the other main component is this. This is the particulate matter sensor. It's from the brand Sensorion. Again, there are many particulate sensors in the market. The reason why we chose this one, we've tried most of them, or most of them. And the reason why we chose this one is first because it's one of the smallest ones. So if citizens need to be able to carry the sensors around, it has to be easy, as small as possible overall. So some of them were like this size compared to these. So it's small, but also it provides better quality data. And what's most important, especially for our level, we want to be able to compare data from street to street. And for that, all the sensors, we need to make sure that all the sensors are coherent to each other, that the data is going to be compatible and comparable. And these sensors come pre-calibrated, and we've done, Sebastian showed you before, that we did what's called a co-localization. So we put all the sensors together on top of a reference station, and all the sensors show exactly the same readings. So that's what we need. We need that if you place sensors together, they are going to read the same thing. So the data is going to be comparable. And this sensor is very good at it. It also have, it's a very durable sensor. It doesn't get clogged. It has like a self-cleaning function. It has like a fan inside, and it's gonna at the beginning start cleaning all of that. So you will hear probably the fan turning. That's for this. Then we've got storage. That's a small SD card module when you can plug an SD card. And the storage, that's as everyone may have used in any computer. You just plug an SD card, and then you can take the data out with an SD card reader and plug this in the computer and get the files in the form of CSV, so normal Excel sheet, and analyze the data from there, or upload that to our data platform. It's a good backup, so all the data is always saved independently of transmission. We have a display. So this is to be able to see real time what's going on. If you turn on the sensor, you can see all the readings in here. And then this is the other VOC sensor, the small CO2 sensor, gas sensor I talked about. It's from the same brand. This is more an experimental module we wanted to try, because for now we've been focusing on particulate matter. We also have some power modules. So this is a small converter, voltage converter, to step down the voltage, because some modules need 5 volts, which is what's provided by a normal power bank, but some of them need 3.3. So this is taking it down to 3.3 volts. Again, we chose this one because it's very small compared to other ones that are much larger in size, and we want to optimize the space. And finally, we have this module here. This is both a GPS and a SIM card module. So this is able to get the location of the device, but also transmit it via the 2G network. The location GPS, we need to take into account a few things. First, we need an antenna, and this will need to be plugged, and the antenna will be able, the bigger it is, the easier it is to detect satellites. We found out that the cable is important. So this cable is quite short, but there are some that are much longer. For example, this antenna here is much longer. So the longer it is, the more interferences it can have. So it's better to get a bigger antenna and a shorter cable. And that's gonna be able to detect at least 3 satellites and calculate location from that. Then for the GSM, you also need an antenna. So this is the one for GSM. And there are a few considerations that need to be taken into account regarding transmission. So I showed you there is this, for transmission, we have this 2G network, so normal like data as in our phones. We have this Bluetooth module here. And there are other options we've tried. I know maybe some of you are familiar with some low power, long range wireless transmission, similar to Wi-Fi, but low power. All of those are available options. For now, it's not implemented in this board, but there are some challenges depending. The city has to have a network, established network for it to work. And same with the data, it has a cost associated to it. You have to pay for the data you're transmitted, and that might become prohibitive for both the citizens or the governments or whoever wants to implement this project in the city. So for now, what's for sure is that you can always store the data locally, have an SD card, and you can upload that to the platform at a later stage. For the power bank, there are also considerations in terms of how much power they can provide. So you can always need to check out in the specifications that they can provide up to 2 amps, because the GSM is very, very power hungry. It requires a big peaks of 2 amps to work. So if the power bank you choose is limited to 1, some of them are, then the transmission wouldn't work. I know it's been quite heavy, so please, if you have questions, do ask. Otherwise, I'll continue. Is there any question, Rosa?
No, not any questions. Please feel free to ask anything that you could not follow or anything about the components. We have a question here from Carla. Give me one sec. Let me read it. Where is it? Saying we have some questions now. Give me one sec to read them.
It's fine.
Give me one second. Why can't I? I will activate. Carla, you have some questions, right? You can ask them in Portuguese. I will translate them.
Maria, can you hear us?
Yes, I can hear you.
Good morning. No, for a while we're okay.
There was one question. There is one question from Guilherme. He didn't understand something about the external battery. If he's asking if you could explain that again about the power bank.
Yeah. So if the power banks can provide different currents. It's normally specified, I don't know if you can see, it's normally specified on the power bank itself. It says USB 5 volts, 2.1 amps. So it's something that needs to be checked if the power bank has to provide at least 2 amps if you want to have this data transmission to work, because some of them don't provide enough current for the whole circuit. Does that answer the question?
Yes. Thank you, Lorena.
Welcome. Any other questions before I keep going? We can start with the assembly now.
Have you understood everything about the components? Please let us know if there's any other explanation about the components or about how each one of them works before we proceed with the assembly. It looks like everything's okay, so you can continue.
Okay, so let's start now building, and we can probably share at some point the screen of the Fab Labs that have components, so they can see what they are doing. So it should be pretty straightforward. So for example, the microcontroller, where do you think it goes? There are like only one place where it fits, and it indicates in which orientation. It could be like this, it could be like this. It's indicating the orientation with this drawing here, so it should be plugged in there. we can just plug it in, and it should be fairly easy. Everyone can do it, even if there is no knowledge about the electronics. Similar, if you look at this, it says here SD card. So we introduced before the SD card module. It's this one. It has a slot here to plug a normal SD card. So that's, again, there is a drawing showing that it should be in this direction and not in this direction. So it can be plugged. And little by little, we can go like this with all of the other ones. So for example, the small step down here, there is a 3-pin slot here. It says step down. And again, there is a small box towards the right that shows that it should be like this and not like this. So it shows the direction. And you can plug this here. Okay. You can see there are 2 pins here as well. That's the, I don't know if you can see these 2 pins here. It's the same as the power bank in case someone would like to use batteries instead and they need some sort of connection here instead of the USB. That's also an option. That's not something to be plugged for now. Then we see this display. There's a name here. Here it says display. 4 pins, similar approach. It doesn't go this way, it goes this way. So little by little, we see that the board starts being assembled, and it's fairly easy. The GSM and GPS module, you have to be able to read what it says. So here there's a small connector. I don't know if you can see in the camera. I'm pointing here, this one. There's a small connector that when you read, it says GPS antenna. So we've got the GPS antenna. I need to plug that in. It should do click. Okay, so now it's plugged. And we could do the same with the one for data transmission. So there is another slot that says here GSM antenna. Like this. And then it's ready to plug. There is another one, but that's for Bluetooth, but we're using a different module for that. So it's meant to be plugged the other way around. And there's a slot here that says SIM GSM, so that's where it should go. So now it's getting bigger. Can we get the camera a bit, oh, sorry. A bit further. So you can see the overall, okay, the overall sensor. And this as well, VOC should be plugged here. Like this. So that's everything that is very straightforward to plug. We have now the PM sensor. If there are any questions or if anyone had trouble with plugging all of this in, please let me know.
Not for now. Not for now.
Okay, good. Okay, now for the PM sensor, you can see on the right side. Let me see. Okay, now can you see my mouse? No? Okay. So you see on the right side in the slide, there are some indications about the PM sensor. That's why when you buy it, you get this only. So it's this green little box, and it has a connector there. So it's not something we can get pins straight directly in. So we do need to get something, a connector that looks like this.
Lorena,
Yeah.
I got a question asking if you could show again the antennas connections.
Yeah, sure. So this is the module, and it has some 3 small golden rounds, and it's written on the board itself whether it's GPS or GSM. So if you look at it like this, there is GPS one is written here, is the one next to the yellow pins. If you look at it like this on the right side, and that's the bigger antenna. If you can think about it saying you're trying to detect satellites, you want the biggest one to try to get more angle to see them. And it's plugged. It's a connector that is round like this, so it should fit in and do click like this.
They got it. Thanks, Lorena.
And then similar, the other one is in the opposite side. Oh. This one is resisting. Okay, never mind. Let's do without for now. So if you have a look to the PM sensor, as I was saying, it has this. I'm gonna move this away for now and focus on this. We have this sensor. If you place it like in the picture, the diagram in the slides, basically we put these squares down and the connector on top, like this. So then you would see that these cables is the ones you would need to connect inside. It's a connector like this. So you need to plug it in, and it will go in automatically. But the thing is that these cables, as I said, are not provided with the sensor. So you need to build your own. So I think the ones we sent to the Fab Lab looks like this. We have cables,
Lorena?
individual cables. Yes?
They are asking me if you could show the cable assembly for the PM sensor.
Yeah, that's what I'm gonna show now.
Okay, perfect.
So I believe they've received, you have kind of these cables alone, and then you have these small connectors like this. The way to connect like this. So you need 2 connectors and 5 of the black cables. The way to plug these connectors in, it's shown as well in the slide. They have like a very, I don't know how well I can show this in this camera. I don't think I can show this properly. Can you see that these connectors have, say again? Yeah, the slide is showing it, but I don't know if you can see exactly. Can you see that? There's normally okay. There's this on the top of the slide. There's this small gray connector that's at the end of the cable. So at the end of the cable, there is this small connector, and it has like a small tab on it that fits in the it's not visible, is it? Can you see that it has
A little bit. We can see that it has some holes, right?
yeah, it has some holes that have the shape like on the top one. So you need to make sure that on the picture on the top left of the PowerPoint, there is the small tab on the cable has to fit with the upper part of the connector. It's not very focused. So okay, so there is a small tab. So if you see here, the top part should go in there. You don't see anything. No. Can anyone give a hand? Maybe focusing the camera. So this should go like. Yeah. Go ahead.
I just wanted to say,
It's not very visible.
it's not very easy to see, but if you look closely with the cables that you have, you notice there's like a small tooth on the top of the flat side, a really tiny tooth, like less than 1 millimeter across, and that tooth has to grab onto the little the side where there's a gap on the top there, like where like the piano keys are, if you want to see it like that. And there's a little tooth on the flat side here that goes in, and then you should hear a little click once you push it all the way in. I hope that made sense.
There is some question here that says the connectors of the cable are facing the same side. Could you compare both sides after assembly?
I didn't quite understand that.
I also don't know what does it refer to. From the Fab Lab side, where you like, could you respond in the question box if you were able then to plug in the way they just showed? Did it work with the components that you have over there?
There's a way of having like a laser to show, but I don't find it.
Or could you please, Tiago, could you please specify or give more details about the question that you just asked regarding the connectors to the cable?
Can you see my mouse now?
Yes.
Yeah, very small.
Yes.
This top has to go on the very top, so it has this shape with a small like top in there, and the small like tooth here has to go in that direction. And the way to plug that then is like if you put, and it does make like click when it fits properly. It does make click. And if you plug that now in the sensor with only one cable in, okay, you can plug this and it will fit. So if you look at the diagram, this diagram here, you place the sensor like in the diagram. And you know that the first cable has to go, it's pin 1, and pin 1 is the supply voltage. It's gonna be 5 volts. So if now you come to the board and do the same thing, you plug. That is a bit hard to explain in a video. So if you plug this one in the other side where it has to go, you will notice that there is this 5 volts sign here. So that's the pin 1. That's the first one we see here. This one has to go, the other one, sorry. Let me check. So if you plug this one in, this one has to go to the one that it's saying the 5 volts. You see in the slide here, the side that says 5 volts. So you can plug it in. And it does a small click. And once one of them is done, all the other ones just follow in the same order. So then you don't need to be careful anymore. It's important to get this right, otherwise the sensor is plugged the wrong way around. Can anyone, is the Fab Lab, did the Fab Lab get this?
Yes, they want to ask you directly. So
Everything
Carla?
is gonna be, yeah, we'll have like assembly guides on the GitHub. I'll show the GitHub shortly. So if this is not working right now.
They say that they already connected all the cables. Carla, do you wanna say something?
How to connect? No, Lorena, we just was trying to get information about the what is the pin 1 and 5 reference at the board. But Lorena just has just replied. We need
Okay, so the 5 volts, yeah, that's this order, yeah, that's the connection. So you see here, the pin 1 is 5 volts, and that goes to the 5 volts in the connector.
Great, thanks.
Okay, good. And by the end of it, yeah, it should look like all of them are connected. And when you plug this one in, the cable that goes to 5, it's the one that is the first. So it's fine. So it's the one, if you look at the picture, as in the picture, yeah, this is the one that is connected to this side. Okay, so that's the more complex part of the whole assembly. And it's unfortunately, it's just because none of these sensors are provided with cables, so then it's build your own basically. But once you have this is all plugged in and all ready. The next step would be to download the programming in the microcontroller. Would you like to go through that? I'm gonna quickly show you our GitHub. So if you visit our GitHub page, can make this a bit smaller. this is the GitHub page. You can see that there is, I'll just move this around for now. Okay. We have everything around. So we have, we've got an introduction to the project, explaining that's a sensor, and it's gonna show at the beginning, very beginning, how to program the microcontroller. So for that, you need to use, we use the Arduino IDE. Do the Fab Labs have the Arduino in their computers? If you could let us know, that would be nice. Can everyone hear me?
Yes, I think they can hear you.
Okay. So there is a few things that are important, and this is all guided here. So you can have a more detailed look later on if you want to. But basically, we use the Arduino IDE. So I'm gonna, where's my mouse? Here. So this is, for example, one of the codes. Basti, if you want to come and help me to do the live demo. So for using this, you can download the code from our GitHub. So as I was showing, this has general instructions on how to do it, but you can actually see all these, the PCB files of the board I showed and previous boards, and all these BP codes are the latest updates of the code. So we are gonna use the version 8 because version 9 is going to be for another sensor. And you could download it here and have a look at it here. So it's the same one I've got open. Everything is on GitHub. You can have a look. So that's the one we have, and that's the one I opened. I have open. If you go to the again main folder, you see that there is a folder called libraries. That's all the libraries you would need to download and put in your Arduino for the code we have to work. And there is another one. This one is a hardware library, and that's to be able to recognize the microcontroller, the black pill that we have. And that's something you need to have so Arduino can detect.
Just one thing, Lorena, I just copied the link to the GitHub in the chat box so that everyone can just click on it and take a look directly.
Yeah, please do. Yeah, so we're gonna show that process of coding the black pill now.
Okay. So okay, let's start from the start. You just installed the Arduino IDE, and then the first thing you do that on the official Arduino website. The first thing you do, you go to the GitHub, and you download. You can basically download the whole repository. But what you will need is the hardware section. Can you see the mouse?
Yeah.
You will need the libraries, and there's a libraries folder. After you install the Arduino IDE, there's a libraries folder created on your PC. You find that folder and you basically copy the everything that's in here into your library folder on your PC. And then Arduino IDE will be able to access the libraries we're using for programming the black pill. And you do the same thing for the hardware folder here. And there's just one folder in there which is called Arduino STM32. And STM32 is basically the black pill. That's the two things you need. You will also need the code, as Lorena mentioned. Right now it's BP version 8. But that's going to be updated. So if you watch the webinar at a later stage, it might be a different one. For example, right now there's already a version 9, which is for a different GPS module that we didn't talk about today. So I think that's the important bits. I will now show you how to connect up the board so you can flash the black pill physically. I'll need the camera for that. So can you arrange that?
Yeah. So back to here and back to
All right, so you will need the black pill, and you will also need this adapter here. It's called a USB to TTL adapter. That's basically because this one, it has a micro USB, which is not in use, it's just for power. To flash the black pill, you will need this adapter to give it power and to also put the necessary code on there. The way I will do it here, you can also connect it via a breadboard, but the way I do it here is I use this PCB that we have with an extra line of pin headers that we soldered on the. If you look at the other PCB which we used earlier, it doesn't have this soldered, but you can solder it yourself. It's just to make it easier right now. So you plug it the way it should be on the PCB here. And then it's important to bring the black pill into flashing mode. And you do that by changing these pin headers. You only have to do that once, the very first time you want to flash the code. And after that, it will automatically boot back into the normal mode. So right now it's on normal operation mode because there's already code flashed on this black pill here. But we're gonna go through the process here. You can leave the bottom jumper like this, but you pull the upper one out and you put them here. If you look closely and you read the GitHub, you will see that these are marked with B+ and B- and so on. You can also figure that out yourself, but just to show it, I will do that here like this. And then this TTL adapter has 4 connectors. It has, if that's visible, ground, 3 volts, 5 volts, and 2 serial connectors called R and T, RTX, RX and TX. So you will need to use this one's better. You will need to connect that in to the connect pins here. You see that the black pill has a ground pin here on the bottom, and then there's a 3 volt pin here. So I will connect that accordingly. The black connection here is ground. I connected this up earlier. Black is ground. Put that in here. Red is 3 volt. I'll put that in here. And then the other 2, as GitHub states, they go in A9 and A10 on the pin. So these are connected here, so the same pins.
So the reason why the problem of the black pill, that's one of the limitations it has, is that it has a micro USB to connect to the computer as a normal Arduino. But the problem it has is that the drivers are very specific to each computer, and most of the times they don't work the first time. So this is a quicker way. Normally, we send you everything, for at least for this workshop, we send you the USB TTL converter, so you can do it like this instead of having to figure out what drivers you need for the black pill. But that's something that can be done, and for the future, it could be set up. It's just very computer dependent. So whenever we run workshops, there's not really the time to troubleshoot if people bring their own computer to install those drivers in each of the computers and get it to work. So we prefer to do it this way. But feel free for you to, there is plenty of tutorials online. Feel free to try to find the right drivers for your own computer to connect the USB, the micro USB to the computer. But this is a very secure way of doing it.
So depending on how much time you have in the workshop, you might be running, you will want to pre-flash the black pills because it takes a bit of time to get the connections right. But it's just these 4 cables going into the right pins. You make sure this is on I think, no, this is actually not.
I think there are some questions. Yeah, go ahead.
Yeah.
Let me quickly finish this and then go through the questions. Okay, so you basically plug this into your PC, into USB, and you will see the black pill will turn on. It will flash red. You click reset here, and basically it's wiped. And then you can start flashing the code. And I will show you in the software in a second. But first, let's answer the question.
Yeah, there are two questions. Three, actually. Does anyone have a pinout of this connection? That's the first one. Why do not use the micro USB connector? That's the second one. And how do we calibrate and validate the data collected by the device? That's the third one.
Yeah.
Question one, why can't you use the USB on here? It will, if you use the USB on the black pill, it will power the black pill on, but it will not set it into the mode so you can flash it. And that's driver dependent on your computer. But it's not very intuitive not as intuitive as you might think to just plug it into micro USB and flash the black pill. That's not going to work. That's why we're using this TTL adapter. So if you, as Lorena mentioned, if you want to try and get this to work, feel free. But in our experience, it's much easier to do it with the TTL adapter. Second question, forgot the second question. The third question.
There's another question from the Fab Labs, which is, does anyone have a pinout of this connection?
Okay. The pinout is on the GitHub. So basically this page that I have on the slide here is just the front page of our GitHub.
I also posted the link in the chat if you want to have direct access to it.
Yeah.
So there is a page called.
No, you can just scroll down.
Yeah? No, that's not the pinout.
Oh, the whole pinout of the black pill.
There are instructions of which pins are the ones that need to be connected. It's called PA9, PA10, and that's written on the black pill itself. So you see the A9 and A10. So you can hear an instruction on how to flash the black pill. But if you want the whole pinout, each of the codes, so if we are now to use this, for example, it has the pinout, and we basically have the picture of the black pill here, and it says all the pins it has and which ones are we using for the connections. So in this case, the two that are relevant are these serial ports here that are meant to be for the TTL, so are meant to be for the flashing. Are these PA9 and PA10, but we do say what's connected where. So for example, here the SHT is the temperature and humidity sensor, the GPS is plugged in these pins here, but all those connections are done internally in the PCB. But if you want a whole pinout, here you can find it.
And after, we have another question, which is not from the Fab Labs in Brazil, which is, how do we calibrate and validate the data collected by the device?
Yeah, so
That's probably for later.
Yeah, we were gonna have a quick discussion about that later, but in case we can answer for now quickly. We showed that already in the initial presentation. So you see, if city has a reference station, we recommend that if you can get access to it, this kind of study is called co-localization study, which means that you just place in the same place all the sensors together to be able to compare the readings of one or the others. So this is the calibration we did for Argentina, for Buenos Aires. So we got access to the US Embassy reference station, and we placed all the sensors on top, so you can see them here. And you leave them for a period of time The longest, the better, but it's not always possible. So in this case, we did a night. Ideally, you would like to leave it 1 full day or 2 to 3 days, if possible, recording continuously. And then you can actually check the data of the sensors, and that's what we did here. So and compare it to the US Embassy. First, you need to compare two things. You need to compare how do the sensors look like, one with each other, and actually they need to be measuring the same thing if they are placed in the same location. And if there is a spike, all of them need to show a spike. So that's the first thing to prove that the data is good, is that the data is going to be comparable between sensors. And that's the first thing you have to do. If you don't have access to a reference station, you do that anyways. If you do have access to a reference station, then you can also compare that value to one of the reference station. And that's what we did in this graph. So you can see that the yellow is the embassy, the reference station, and in red is our sensor. And you can see that they actually really, whenever there is a spike, they're really similar. Whenever there is a spike of the reference station, our sensor also records the same spike. And that's the validation, the data validation we need.
I think for the sake of time, if you want to look at that again, just go back into the recording of the webinar and look at the graph in detail if you like.
We're going to share all of these slides, and we're going to share the video later on, and you can have a more detailed look and always ask more questions. But there's the way of calibrating the sensor. They are pre-calibrated already.
Yeah, I think it's important to know that we picked the sensor, this green little Sensorion sensor here, because it's pre-calibrated from the factory. We work with other sensors which were not pre-calibrated, and it's a huge pain. So this sensor is actually very good at that. So if you just deploy a few sensors, accept that they are pre-calibrated and do a co-localization, but it's really hard to gain access to reference stations. It's great if you can, but it's not a must.
Yeah, it's not always possible. Some countries, when we went to Kenya, there was just no reference station available. So we did the co-localization to check that all the sensors were coherent to each other and validate that. So we are not aiming to provide absolute values saying, oh, this sensor is saying that it's measuring 30 micrograms per cubic meter of PM. We want to compare values. So we are interested in the relative differences from street to street, so you can see which places are hotspots compared to others. So it's all relative. We are not a reference station. We are not at the reference level. We are indicative measurements. But as long as all the sensors have the same trend when they are placed in the same place, that's already showing that it's good for the purpose we have. All the sensors are going to record the same, and they are coherent to each other. And that's the validation.
Okay, I think just to stick to our timeline, we should move on with the flashing quickly.
Yeah. So we'll just go back. Is that answering all the questions? So do you have any other question?
No more questions for now.
Good.
Okay, so back here.
So as soon as we connected everything up, we plug this in, the black pill is on, we press this reset button, and it's ready to flash. Then you go into the Arduino software, which I have on the next slide. Lorena, I think I need your help. I have the software here on this slide. I booted up the software. I loaded the black pill code, which is you click on File, you click on Open, you open the code, and it should show you something like this. Relatively long code already because we have a lot of modules in there. But it's nothing to worry about right now. First, you need to set the software so it can properly speak to the hardware. And for that, you click on Tools in the top here, and you select the board you're connecting to. And if you did the hardware step right, remember when I said copy and paste the library and the hardware folder from the GitHub repository to the local folder on your computer. If you did that right and you restarted the Arduino software, you should see the supported board here, and that's the one you need to select is generic STM32 and then 103C series. You select that over here. Make sure this is selected, should be auto-selected. The uploading method is also important. You need to change that to serial. By default, it's set to something something else. You did? We don't need to, I think, but it can.
So you show the options. So it's in tools.
I think no, the camera is in front of it, Laura.
Oh. What am I doing? Okay. So in tools, yeah, there are different options.
Yeah, you select the board here. Some black pills have 64 kilobyte flash, some have 128. It should, version 8 should work with all 64 kilobyte boards. So you can set it to 64. If it doesn't work, set it to 128. But 64 should be all right. This can be left at default. And here, this is very important. You need to set this to serial, the uploading method, because we're uploading via RxTX, and these are the serial ports. That's just how we connected up the hardware. Rest can stay the same. The port, make sure you select the right port. Here it's one of two, one is inactive. I haven't plugged it anyways, but as soon as you plug it, there should be an extra port here. And it's if you struggle, just try all the ports, click upload in the software.
Sorry, they are asking me to return to the Arduino configuration steps, the slide before, I think.
Okay.
Let me activate.
That's just GitHub.
Yeah,
give me 1 sec. I will activate them.
I think I want this.
Carla or Thiago, you have a specific question here.
Yes. Just the point that we need to see that steps, the B and C, because we were solving some issues with the cables, so we need to prepare the Arduino IDE.
Okay.
So basically, I'm talking over step B right now. And what I did on the hardware with this connection is basically step A. Step B is in the software, and step C is automatically executing the code after that. So everything I say is in short within these few lines on GitHub there.
Do you have any other question on your side, Thiago or Carla?
No.
Okay, good. So we can continue from here, right?
Okay,
Just regarding the missing components that we noted here, one of them is the step down module. I believe that without the step down, we cannot power on the board.
No, because the microcontroller needs 3.3 volts.
in this configuration, you can.
If you use, do you have the TTL converter?
We can use the TTL converter to supply.
So the TTL.
Okay. For the programming, okay, we understood.
Okay.
For testing, we can try to do the test with the using the TTL converter as a step down.
So what you can do, you can so the TTL has 5 volts as well.
Okay.
You will need 5 volts to power the PM sensor, because the fans just run on full on 5 volts, and otherwise it will change the reading. There's no way around that. If you don't have a step down, it's going to be hard to run both. But you can hack your way around it if you want.
No, I think
If you have 2 sources of voltage.
Can you show the board, the connector of the step down? Yes, these three pins. If you give the pin out of this connector, we can connect the pins from the TTL converter to this.
Yeah. So basically, the step down, the top pin, so like this.
Okay.
The top pin is 5 volts.
Okay.
The middle pin is ground.
Okay.
And the bottom pin is 3.3 volts.
3.3 is the pin close to the switch.
To the display.
Okay. Please.
The closest one to the display is 3.3. Fantastic. That's like VR.
And the 5 volts is the close to the switch.
Yeah.
Yeah.
VO is V out, right?
Yeah, so yeah, VO is V out, VI is V in.
Yeah, that's fine.
Yeah,
it's fine, it's fine.
That's fine.
Yeah, so that's the connection. So you can plug from the TTL converter has a 3.3 output, so you can use that and plug it into the 3.3 inlet. So in this case, you have this, they have a 3 volts. So you could plug the 3 volts of this onto the input here, and that would plug the whole board at 3.3.
This is a 3.3.
I think it's 3, but it should be fine, 3 volts.
Okay.
So that's a way around it for now.
Yeah,
yeah, there should be more step downs at the Fab Lab Newton, I think.
Okay, we will use the TTL converter to perform the test, and after we buy the step down modules.
If you're not so concerned about power, you should be able to get linear regulators as well with 3 connectors.
For now, it's for now for the board.
But for now, yeah.
So let's quickly flash the black pill so you show the receipt.
Yeah. So if you go back to the software, I will back into the software. I got it. You have the code here. You did all your pre-settings and tools, and then this here is verify, which just verifies the code. If you click, it basically compiles the code. If you click upload, it will verify and upload the code. So upload will then start. We don't have anything connected right now. I will just verify, which basically looks the same. You see this bar here progressing. You see that the sketch is compiling, and you will see a percent ramping up here to flash it. Do you want to flash it now live?
Yeah, because you need to flash the receipt.
Yeah, I mean, I did tell 2 times too. So, yeah, you don't see the camera right now. Turn it on again. Yeah, I'm going. So I plugged it into. I plugged it in now into the computer, and you see the black pill is on. You see the red light. I click the reset button here, and it's reset. The next thing in the software, I click on upload. Should check if the right COM port is selected here. Yeah, you see a third one appeared, which is COM19. That should be the correct one. Selected by default. and I clicked upload, and now it should be compiling and uploading the sketch. Make this a bit bigger.
So it's important to press reset before on the board before doing that, otherwise it won't work.
And there's an error. So yeah, Lorena doesn't have all the libraries. So that's the first mistake you can do. That's why I wanted to avoid a live demo, because it never works. But so we didn't do our homework and we didn't put the libraries on. But it should, if you just download the libraries from the GitHub and copy paste them, it should work. But that's basically it. And now it's really important.
Sorry, just one question. He said that he's trying to download the library. If you could show again what's the correct one.
All of them. You just copy and paste the whole folder over.
Everything that is in GitHub is the correct one.
Okay. Did that answer your
I show you the process quickly, since we don't have it either. So
I think we do.
there was some. So I think the display library was missing. Your mouse is hard to see. Okay, okay, I got it. So we're on GitHub. This is the libraries folder. You have all the libraries in here. And we were just missing, I think, this library here, which is for the screen. What I'll be doing now is I just download the whole thing. I download it zipped. And it will appear here. Downloading. Just open the normal screen. So there's the GitHub. Download it. This folder here is the libraries folder, and it contains everything we need.
If you could, they are asking me if you could do it a little bit slower so that they can follow up at the same pace as you are doing it.
Sorry?
If you can do it slow.
Slow, okay. Basically, I just downloaded the whole zipped repository from GitHub. It's in the upper right corner here, clone or download. And now I went into the zipped file, which I just downloaded. And there's this libraries folder in there, which we need. Same for the hardware folder. And now I'm looking for a local folder of Arduino, which is typically in documents. For me, on this PC it might be different. Otherwise, it's in your programs where the Arduino IDE is installed.
You can also just do it. Is it visible? No.
No.
So if I go to that's depending on each of your computers where you download, where you have the Arduino folder. Mine is in the disk C where all the programs are installed. I have Arduino, and there is a folder called libraries. And you open that, it has all the libraries that are installed in the Arduino, and you can just copy paste here the ones from GitHub. and then that should directly add all the libraries in Arduino. So the ones from GitHub, where did you put them? Are
No, go back. The zip folder was open. No.
here.
Yeah.
So these ones are all the ones from GitHub. So that's just the folder of OpenSeneca in GitHub. We downloaded everything. So this folder here, you can open and just copy all of these ones. Copy to the Arduino folder in your computer in the libraries folder. So and I do have already some of them because I downloaded these. I just replaced everything. But that's the way, it's the standard way of installing libraries in Arduino. So once you do that, when this is finished, the only thing we need is to, yeah. Now the only thing we need is to close. So that's for the software ones. Then there is also the hardware one, which if you go back, it has to be able to recognize the board. There is this hardware folder here. And same, you need to copy that. This folder here, you need to copy it into the Arduino hardware library folder. So that's, again, if I go to my normal, so I've got Arduino in my programs. I've got Arduino here, and there is a hardware folder, and it will have all the normal Arduino boards, and that's where you copy the Arduino STM32. That's our board. You just copy it in, and I already have it, so I'm not gonna copy it again, but that's the same process. It's just a different folder. And in the moment you do that, then if you restart Arduino, so if we come here and we close, and then restart again, I'm restarting Arduino, it will be incorporated. All the libraries will be incorporated. It's loading. Were you able to follow this, or was it too quick?
I were following up with them, and we say that we were following all the instructions. A couple of minutes ago, they were still downloading the libraries, but they were following.
Yeah, we can do that. We can follow up on that, but we can move on because we're running out of time, and we still want to talk you through the data platform, how to use that. But it's all of this is, as we said, documented in GitHub, and yeah, the way of flashing it, as we say, once you have all of that, you should be able to see there should be this board that appears, the generic STM32, as Basti was telling you, and then all the libraries should be included. If you have any problems flashing the board, please let us know. We can follow up after this webinar more individually with the Fab Labs and with Thiago, whoever has sensors. But for now, we can keep going. So the important bits to remember for this is that you have to press the reset button in the black pill as you flash. So, so just checking, so the port is still there, and then you need to press the reset button as you flash, and that enters the black pill in the correct mode for flashing. Otherwise, it's not open to be flashed. So now it's still compiling. Can show the camera back again. And well, it's taking a while, and then the other important bit to remember, as we said, is that once you're finished, you need to move back this yellow jumper following the instructions in GitHub. So the instructions in GitHub are saying that you need to put it back B0. You need to move the bottom one. Yeah. So you should basically okay, so that's how it should have been for the programming. That's the thing that why we're having the mistake, the error. So we try last time, we press here. Yeah, and now it worked. Did it?
Yes, it did.
So okay, so the pin was in the wrong, but that's specified in GitHub. This jumper was in the wrong. So once this has worked, it's uploaded. We move it back, so that's like the running mode. We move this back here, and the black pill is programmed. So now we don't need to flash it anymore, and we can put it back in our board. And just put it back to the other board. You can also do this as fast as just on a breadboard. You can just plug it in to access the pins, or get some pins onto this one. So now, just quickly finishing this up. If we plug the power in, so we can go have a cable for a power bank and a power bank here, so at least you can see something. Working. Is that not the right cable? And we switched on. Oh, yeah, fair enough. We're missing the step down. Is that the right cable for it? What's this not turning on? I think the power bank might be, this one might be this, oh, now, okay. So sorry, the power bank was not turned on. So this has to be on, the switch and the power bank switch. And you can see now that the black pill turns on, the screen turns on, and it's gonna be writing, for now, OpenSeneca, quality sensing powered by city science, and then it's gonna start reading values. You will hear that when you do that, the fan, you can actually hear it turning and see, I don't know if you can see it's turning, but you can hear it as well. And it's gonna, for now, it's initializing everything, and it's gonna start reading values very soon. So that would be hardware-wise. Once you do this, is everything okay? Can we move forward to the, can we move forward to the data visualization? Because we are gonna, this book we're in is gonna be booked in 10 minutes at 3. So we need to move on. Okay, so I'm gonna close this for now. So there is a bit more about all of these we're talking about. That's the code itself. It's pretty self-explanatory. See, here it's reading already. So we are reading the values. You can see them in vertical, and it gets updated. So I'm gonna hand over to, there's a few considerations about the case. The most important one is that there is no, you need to avoid direct wind in the inlet of the sensor. So this is, it has a fan, so the air is coming in here, and it will go out there. And the way you need to design this, that there is no water or dust has to get inside the box, it has to be waterproof, but it has to allow air inside to have this, to get access to this. But if you get direct wind, that's gonna give you wrong measurements. So we have a few designs. You can see one here on the slide. So for example, the PM sensor is meant to be, I can show you here as well. This is one of the boxes, for example. Let me bring this camera up. So this is one of the boxes. So for example, the PM sensor will be here. And you can see that this is directing the air inside the inlet and the outlet. So it's protecting it from any rain. This is meant to be like this. So if the rain comes in, it's not gonna go in. It's protected from the wind, but it's allowing air to go in, and it's gonna be sucked by the fan. So I have a few considerations about that. There's a few considerations about the mounting of the sensor. You need to have some parts that are accessible, so it has to be able to be turned on and off. This has to be accessible, the SD card as well. That's why it's all nearby to have access to it. It has to be robust. So we found 3D printing is very nice for prototyping, but it's not as nice in terms of having a sensor around the city. So we've also been working with this kind of junction boxes that are meant to be for electronics. And this is meant to be mounted like this. So you can see that there's an outlet and a hole here for the sensors to get the air, and the charger is coming here for the power bank. But it's allowing air, but it's again protecting it from direct. If it rains, it's gonna come here and not inside, and it's protecting it from direct wind. So that's also an easy solution. These boxes are very cheap, are like $5. So it's an easy solution to use something that's readily available instead of having to design something on your own. And then in terms of the platform, quickly, Charles, you want to talk through this? So I'm going to introduce you to Charles, who was missing before. He's the person who's designed all the platform. Where am I? Okay, I'm going to stop this now. Okay, so we can do a live demo as well if you want. The platform.
I think at first maybe just very briefly going over the slides.
Okay.
So yes, hi everyone, I'm Charles. As Lorena said, I mostly work on the software and the back end. We'll see a few of the features we have on the platform. At first, you can already go here and register. It's free and only takes half a minute. In this form, where you put your account name and email address and so on, there's also a box where you can put a SIM number if you wanted to feed GSM data into our database and later look at that. I'll just skip through some of these slides because I think we don't have time. The platform has a file manager built in. Once you've registered, you will see just one file. This one file it's showing a trail of data that you can plot in 2 different ways. We can go and have a look at it right now. So here I've logged in with, I believe, Lorena's user. And trying to find out where the mouse is. Here it is. If we go into the file manager, we'll see a bunch of folders and files. And we can upload new files by clicking this icon in the upper right. If we go back and look at some of the existing files, we see these icons to the right. If we click one of the first 2 icons here, we'll see a visualization of the data in that file. So this first one seems to be from Paris, and we can see the entire trail, zoom in, look at where there might be some highlights and so on. If we go back, we could also, with that same file, look at the time series. So that's the icon right next to it. And we can zoom in if we want to look something more close up and inspect the values at any point in time. So it's really quite easy to use the file manager. As for the other features in the platform, you can communicate with other users. You can do it via email or via a personal messaging system there's built into this platform. So you'll see the different users here, and you can contact any of them if you want to do that. One of the essential features is that you can address other people's problems if you know their solution, or you can ask for help in the forum. So you would go and make a new thread for some issue you potentially had. Finally, there is one more thing I would like to show you. If you register and you put in, we can try to log out here. There. If we were to register a new user, this is the form. In the lower left, you could put in a number to identify a SIM card that is set up with our database. Later, you would then be able to see that device. Where is there? Should work? Nope. Lowercase. We'll of course share the links to these sites with you. So here's a list of different SIM cards. If you had put in a specific SIM card number into our portal, you can open up this link and you'll see different ways to export or visualize the data from from that device. With this one, I'm not sure there's anything interesting here, but we can have a look here. A nice thing is to show the table that's in real time. So this will update by the second without you having to reload, and you can just look at all the data coming through. You can export to CSV, you can plot it immediately. So yes, that is the things I wanted to say about the platform.
I would encourage, if you have questions after this, because we're running out of time, make a user in the forum and ask them in the forum. Maybe you can even answer the questions of each other in the forum. So we get some activity in the forum, and also people can read your posts and then might have the same questions and they're already answered. So that'd be great.
Yes, indeed. If there's anything else right now, I'm also happy to take questions. Whoop, that was
yeah, that was a bit to talk about workshops. I guess all of you are experienced organizing hackathons and workshops. We found that that part is probably okay. This was gonna show a video that was recorded about the workshop the people in Nairobi organized. So we basically what we're doing in this webinar, we did that in person. So we went there, worked with them for a week, built the sensors, and then they organized this workshop on their own. I think there's some tips that were actually important or we learned from these workshops, is especially keeping a record, how to choose volunteers. I believe in Belo Horizonte at the beginning is going to be with cyclists. We've been mainly working with cyclists so far, but in Nairobi, they try to mount sensors on cars as well. So there are a few considerations to take into account in terms of mounting, but it's important to record which volunteer has which sensor. So Charles showed this box, the sensor number that you need to enter. If one of the volunteers, when they register in the platform, they need to enter that, so we know who has which sensor. And also having some sort of agreement with them, so they return the sensors back, or they know what they should do. And in terms of maintenance, have a local person of contact that knows how to build the sensors and know how to troubleshoot, so they can bring the sensors back if they have any problem or something that is not working. That's actually quite important. I don't know if you want to have a look to this video. We'll share all the slides, but that's summing up what happened in that workshop. But as I say, I think most of you are experienced organizing these sort of activities. Is there any questions we can answer now? So just go.
Not really. Not really.
Okay.
Maybe they have a few questions actually. Just replied. I don't know if we do it now because they might be very specific to the sensor, or if you have a few minutes, then we could finish the webinar now, and the specific questions we can do it bilaterally.
Okay. We might need to leave this room empty because there's gonna be a lecture soon. But we can, yeah, if there are general questions, we can wrap up. If they're very specific, we can probably, I can stay a bit longer and discuss the answers. Yeah.
Perfect. Then I will just send you the link for that. Then thank you very much all. Thank you very much to the OpenSeneca team. It was great. We hope that everyone who was on the other side was a little bit able to follow. As I said at the beginning, this is an experiment that we are just trying to see if it will be possible to have this type of trainings, online training, so that Fab Labs on site could implement this type of workshops. Let's see, we will tell you about the results. But the idea is that because this is an experiment, we've also created a survey asking you some questions related to the webinar, related to the things that you learned, related to your capacity, or if you were going to be able to really build these sensors afterwards if you had the components, and how difficult would it be to have the components or to get the components on site. So please fill in the survey. That would be great. It will really help us improve the content of the webinars, make it more personalized to or tailor-made for your needs, and also to create new content that would allow you to adjust, adapt to the context. So please, 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 it would be great if you could fill in the survey and follow us, and to know more about our following webinars. The next webinar will be in April 8th about how to use the sensors, this type of sensors. We have some case studies with fixed and mobile air quality sensors that you could see. So thank you very much all for attending. Thank you to the Fab Lab in Belo Horizonte for putting all this effort, and we'll catch up with them for specific questions afterwards. Thank you very much to all.
Thank you.
Bye.
Thank you.
Bye.
Bye-bye.
Bye-bye.